Good. So, sorry I couldn't be here yesterday. Lev and I go back a very, very, very long time. And just to kind of set this up, as you would expect, when we first started arguing many decades ago about many worlds, most of it was on probability. We're going to talk about a lot. And so I argued with Lev about probability and argued with him about it. And then I remember we were in Sesto, and I said, Lev, there's this other problem. Doesn't have to do with probability. And we were walking up in the Alps, and Lev kind of freaked out. Because he said, no, because he said everybody agrees if you're in an eigenstate, you make a measurement, then there's no problem. Then many worlds is perfectly fine. The only issue is if there's splitting or branching or whatever. I said, no, there's this other problem. Now, this had been impressed on me by Shelley Goldstein, and ultimately, it's all in Bell. So most of this talk, as you'll see, is about what half of my entire career has been, which is just expositing Bell, and with a few minor variations, and maybe to make some distinctions that will help connect this with what some other people say, which is very similar, and I don't know if there's any deep disagreements. So this is just to begin. What I just said, okay, we can worry about probabilities in many worlds, we can worry about fissioning, we can worry about personal identity, blah, blah, blah. I'm just going to mention here, because for me, this is hard when I go back and read Everett's original relative state interpretation. I don't see much of what now called many worlds. All right, but anyway, I don't want to get into that. So you have this problem about probabilities. I'm not going to talk about that. I want to talk about this other question. And it's going to be completely independent of that. The manyness of many worlds. The manyness of many worlds is not going to be in this talk. The question is whether there's any recognizable world at all. All right, so if we just walk our way back in history, one of the things that's usually said about quantum mechanics is that how does it depart from classical physics? Somehow the observer, which was expunged by Newton and Maxwell and so on, becomes central to the theory again. That, of course, is problematic because then, as Einstein pointed out, who counts as an observer, right? Is a mouse an observer, and so on. You can try and get rid of that problem by saying, well, it's just a question of measurement, and measurement doesn't require an observer in any fixed sense. It just requires some kind of coupling between two systems that can reliably create a correlation between them. The more radical approach, which is usually associated with Wigner, is the idea, no, you really need to talk about an observer, meaning a conscious observer, meaning you have to talk about conscious experience somehow in order to understand quantum mechanics in a way you don't need to do in classical physics. Now, many years ago, there were a set of, I guess, 3 conferences in Bielefeld that were called Quantum Mechanics Without the Observer, that started, unfortunately, right after Bell died, so there was anyway. And the idea was, well, let's see if we can avoid all of this talk about observers and all this talk about measurement and so on by looking at theories that do not need to invoke any of those concepts in their fundamental postulates, right, in their principles. And Bell has this nice phrase. He says that there are certain approaches that neither require nor are embarrassed by the presence of an observer, right? Which is what we would expect for pretty much all macroscopic objects. You'd sort of like to say classical physics is neither requires nor is embarrassed by the presence of internal combustion engines. Right? The theory makes sense without them. The theory can accommodate them. And similarly for observation and similarly for measurement. And then when you talk about measurement, if you have a picture where you've got these well-defined subsystems that have their own intrinsic states and dynamical interactions between them, then of course you can start to analyze the nature of those dynamical interactions and the sorts of correlations that they might set up between the two systems. And if you do that, then you can start appealing to Shannon's information theory, which is exactly in these terms, to quantify information in one system about the other system and so on. So that's an approach which certainly makes sense. Now, many worlds, as I understand it, and have always understood it, is that it is supposed to be one of these quantum theories without observers, right? That observation, measurement, and so on are not supposed to be playing any foundational role in the statement of the theory. This is now just we're at a conference. If there are people who understand this differently, it would just be worthwhile pointing that out at some point so we're not talking at cross purposes. Still, there's a funny way, and this is now dipping into the thing I'm not going to go into, where something like conscious observers, or anyway, observers with intentions, kind of sneak back in some of the talk about how to understand the probabilities that then make reference to practical decision theory. Because in practical decision theory, the normative rules about how to make decisions are all relative to the preferences and desires and values of somebody. Now that somebody, it's not really important so much that they're an observer, it's just important that they have values, that they can say, gosh, I want to make a decision that will maximize something. And it's hard for me to see how, if you don't have conscious agents, there would be any foundation for these, the valuations that have to go into any practical decision rule. So you might say, gee, at least some kind of conscious agent gets back in the back door. I don't want to, again, that's about probability, and I want to leave that aside. Okay. What I want to talk about is empirical content. Because whatever this theory is, it's part of physics, and part of physics is an empirical science. One way or another, much, although certainly not all, of the grounds we have for taking a particular physical theory seriously as a proposal has to do with its ability to account for some empirical phenomena. And empirical traces back to the Greek empiria. Sorry, they don't let me put diacriticals on these things. Greek readers. Which is just experience. And then you'd say, well, gee, so any empirical science somehow or other has to talk about, at least implicitly make reference to experience. And experience, of course, is conscious experience, as far as I know. So you might say, well, gee, any empirical science, somewhere or other, if you really lay out all of its principles, there does have to be some reference to observers. And on this understanding, which is quite easy to fall into, and if I were to give you a long lecture in the history of philosophy, would take you back to the logical positivists and the logical empiricists and the whole empiricist tradition, where really conscious experience is playing a central role. I mean, Leibniz, sort of all he had at a foundational level are objects that have experience. That's it. Physical objects are somehow constructs out of monads. Anyway, so this is a very quick and kind of compelling argument that says, look, physics is an empirical science. Empirical sciences are somehow about experience. Physics must somehow connect up with experience. Why? Because it's experience that provides our one means of testing the theory. But if you then kind of think through what that would require to carry out, you'd say, now I need to solve the mind-body problem. Because how do I get any predictions about experience out of the kind of description that physics traditionally has given us, say in classical mechanics or Maxwellian electrodynamics or Democritean atomism or what have you. The whole question of how we get from a physical description in the traditional sense to any claims at all about conscious experience is the mind-body problem. And I would claim no one has or ever has had a real clue about how to solve that. Now, at this point, you might say, okay, so throw up your hands. If physics can't make principled connections to experience, and experience is the only test, then physics can't make any principled connection to tests, so the whole thing is some kind of fantasy. That obviously is not right, right? We all know that's not right. The question is, okay, then how does it really work? Not by this kind of simple three-line set of connections. And I just want to sketch out a picture of how at least a big chunk of this works that makes a big difference to how you understand proposal about quantum mechanics. Now, before we get to quantum mechanics, let's talk about Newtonian mechanics with this big picture and question in mind. How can you test Newtonian mechanics empirically if, as is true, no principles of Newtonian mechanics have any implications about experience, right? Nonetheless, we would all say Newtonian mechanics is and always has been extremely empirically successful within some epsilonics, right, within some margin of error. And certainly Newton never solves the mind-body problem in order to do that. And what I'm going to say is just absolutely trivial, but I'm saying it very explicitly to put it right in front of your mind. So how do you empirically test a theory like Newtonian mechanics, all right? So let's just talk about Galileo's experiment. Galileo claimed, and that asterisk is that there's actually a kind of complicated historical question about whether Galileo actually did claim directly or indirectly to have actually done this, or if rather he thought quite reasonably that you didn't have to do the experiment because everybody knows how it would come out. Anyway, he talks about this experiment where you drop a heavy and a light object, one of them a musket ball. I said the other one a cannonball. I'm not sure if that's right. Anyway, one heavy and one light, equal density. From a high tower, this later gets reported as the Leaning Tower of Pisa, but that's not in the original thing. And he says, Aristotle's theory of motion, which says that things fall at a speed proportional to their weight, would suggest that the object 10 times heavier would hit the ground as it were 10 times faster, or as you'd say, if that were right, when the cannonball hits the ground, the musket ball would be way up there. And then the report is, but I've done this, but again, this is in a dialogue, and they hit together at the bottom within a few finger breadths, I believe is the term, right? Very close to each other. All right, so that's what we would normally call an empirical phenomenon. Let's look at the side on which how can Newton explain this thing fundamentally from his principles of physics? All right, so that's easy. On the one hand, you have the law of gravitational force. You assume in the situation, you know there are other forces besides gravity, you know there's air resistance and so on, but because these are musket balls and cannonballs, you think that the amount of that other force is very small in comparison to the gravitational force. So you have this approximately that the gravitational force is approximately equal to the net force, which by the fundamental dynamical principle is ma, and therefore the mo, the m object cancels out, and we get a gravitational acceleration that's independent of the mass of the object. And then you say, well, if that's true, then it doesn't matter at all that the cannonball is 10 times heavier than the musket ball. They should fall together. If I let them go together, they should hit the ground together, right? And that, as we would say, has empirical import. That's the kind of thing you can check by an experiment, right? You can empirically check. How? You go up to the top of the tower, you have an assistant let them go at the same time, you stand at the bottom and see where they hit, right? Now, did that little Newtonian derivation actually result in any claims about experience or observation, right? Where did it come in? And obviously not in the equations, right? There was no derivation of anybody's experience of anything. There's an assumption, which is that people can reliably tell whether two macroscopic objects of this sort were in fact let go at the same time and can tell whether they hit the ground nearly together, right? So if that's true, then you understand how to use the theory to make a testable prediction and furthermore how to test it. Of course, as I say, the actual physical claim that we derived out of Newton is not that this will be reliably observed. It's not that it will be observed at all. This could happen and it not be observed. Maybe it's too dark, right? Maybe you can't see where they hit. Maybe the people who are dropping it and the people watching are drunk, so they can't reliably report anything. Maybe there's nobody around and it's just two rocks that happen to fall off a cliff at the same time and hit the bottom at the same time, at about the same time. You'd say it gets the same explanation. None of the stuff about observability comes into the Newtonian prediction or explanation at all, right? So all the stuff about observation is just shived off and dealt with separately. The physics, of course, doesn't care whether there are any observers around, because we just went through what we would normally say is how we derive the prediction, and it didn't mention any observers, doesn't need to, and they wouldn't make any difference if they were there. Okay, so all of that leads us to a very simple moral about empirical content, which is that if we have a physical theory and we can use it to predict something that we already, quite apart from any physical considerations, accept as reliably observable behavior of physical objects, then we get an empirical and testable prediction. And of course, you know, in the case of Newtonian gravitational theory and the predictions of eclipses and so on, you would say, well, what really goes into the prediction? How far does the physics go? Well, it's going to involve the gravitational theory being applied to the planets and the sun and so on for their orbits. It's going to involve a little bit of geometrical optics, the assumption that the light travels in straight lines from the observable planets to the Earth. Maybe, if you're really fancy, you get into a little bit of the optics of telescopes and do ray tracing through that. One thing you never do is get into anybody's cranium, right? And if this weren't how it worked, physics could not exist. It's just that simple, right? If you couldn't make connection to what we think of as empirical data in something like this way, if you had to go all the way through the brain into and somehow get yourself all the way up into conscious experience, then physics couldn't exist because we don't know how to do that. We don't know how to do it in principle, and we wouldn't, even if we knew how to do it in principle, we'd never know how to do it in practice because we never know enough about anybody's brain to give a relevantly complete physical description of it. Now, so the idea is, look, we start out assuming we know some stuff about the world. Now, that assumption is not sacrosanct, right? We could come back at the end of the day and there could be a kind of feedback loop from the physics and say, you know, some of this stuff we thought that we could reliably observe about the physical world, we actually can't. So you can raise doubts about empirical import. But the logical situation, and this is for the people here who don't maybe have such a background in philosophy, is the one that was described famously by Neurath in his analogy of the ship, where, well, if you don't know, okay, sorry, let me go back. So I think I had this somewhere. But, what Neurath said is we are like sailors on the open sea who have to repair their ship at sea, and we can't take it into dry dock and take it out of the water and then, you know, wholesale replace the entire hull, right? So what do we have to do? Of necessity, we have to keep parts of the ship stable, treat them as stable points that we can use to launch interventions, you know, and fix little problems here and there. And what I'm saying is that we're in exactly that situation. We have to take some of our observations as giving us reliable information about the physical world in order to do physics. That is an initial assumption. It's subject to revision, but only spot revision, and those revisions are going to be motivated by other empirical considerations, right? So you can't just, if you want to go doubt the whole thing, then you're into Cartesian skepticism and you'll never get out of it. So, what are these things? So I said there must be these physical facts that we start out taking for granted that we have reliable empirical access to, even though we don't have a detailed physical account of how that can be. So what sorts of things are prima facie taken to be observable physical objects and behaviors? Obviously not wave functions, or as I prefer to say, and I'll just, you know, I do this all the time, but I'll mention here quantum state. So I make a distinction between a wave function, which is a mathematical item, and a quantum state, which is supposed to be a postulated physical item that is referenced or described by the wave function, and that physical item is supposed to pertain to individual systems. Whether you believe in such things or not, nobody thinks they're observable in the naive sense of an observable physical phenomenon. Why not? Well, here's my first quote from Bell. He says, it makes no sense to ask for, and this isn't even about observing it, right? It's just for the physics to ascribe it. Makes no sense to ask for the amplitude or phase or whatever the wave function at a point in ordinary space. It has neither amplitude nor phase nor anything else until a multitude of points in ordinary three-dimensional space are specified. That's from Are There Quantum Jumps, his paper on the GRW theory. So quite apart from asking, well, could I observe the amplitude or could I observe the phase given what it is, there's this other question, well, but even the phase and the amplitude aren't even ascribed to locations in physical space. And normally, if I'm going to observe something, what I'm going to observe is located in physical space. Now, how did Bell address this problem? He does it in several places. The main place is a paper called The Theory of Local Beables, but then you see content of that paper appearing in other papers, more or less taken for granted. So there are discussions, as I say, in Are There Quantum Jumps, and at least implicitly on the impossible pilot wave. I put those down because among the great competing theories, understandings of quantum mechanics without observers, there are pilot wave theories and collapse theories, and then many worlds. I mean, that's the way I would always triage that. And what Bell does is he says, well, the theory, at least, I'm going to try and state this in the most precise way I can. I know what I'm doing in a straightforward way if the theory postulates local beables in ordinary space. And so what does he mean? Again, maybe everybody knows this, but just to make sure we're all on the same page, by a beable, Bell just means the ontology, right? Something that the theory postulates to physically exist. And the B is it should just be there, right? It is there independently of any observation or anything else, right? As he says, if you even try to understand the way orthodox quantum mechanics is used in order to use the theory in a particular experimental situation, you have to think you know things like the settings of the instruments and so on. So the beables must include the settings of switches and knobs on experimental equipment, the currents in coils, and the readings of instruments. Observables must be made somehow out of beables. The theory of local beables should contain and give precise physical meaning to the algebra of local observables. And you see you're going to be in a whole lot of trouble if you try to do anything else, right? If you say, no, 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 there's nothing, and God knows people talk this way sometimes, there's nothing there at all until something is observed. And then you say, but wait, so was there an observer there who did the observing? No, 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 that observer wasn't there until that observer was observed by a super observer who didn't exist until they were observed by a super observer, and all the bee watchers in Hotch Hotch are watching bee watchers without end. That doesn't make any sense, right? There better be something that's just plain there. Now, among the beables of the theory, Bell then makes a distinction. He talks about the local beables. And by local, he means things that are, can be ascribed to, well, let me go backwards. By Bell's understanding of local beables, the quantum state, this thing represented by the wave function, which he does take seriously as a beable, as something physically real, and it's very hard to see how to do quantum mechanics without taking it to be physically real, a thing that pertains to individual systems. Why? Two-slit interference, for example. So it's not per se, the wave function is not per se a description of a collection of systems. It's not a description of anybody's beliefs about systems. It's not a description of anybody's information about systems or knowledge of systems or anything like that. It's describing something about the system, about the individual system. But he says it's not a local beable in ordinary three-dimensional space.
Sorry, the tech team asked that you talk in this area, so the camera will...
Oh, okay, sorry. Okay, so here's the relevant quote again. We'll be particularly concerned with the local beables, those which, unlike, for example, the total energy, which the total energy is obviously not problematic in any way. It just pertains to the entire universe and not to any subpart of it, can be assigned to some bounded space-time region. For example, in Maxwell's theory, the beables local to a region are the fields, typo there, E and H in that region, and all functionals thereof. That's my chess notation. I don't know why he added all functionals thereof. That worries me a little bit, okay? But anyway, it's in terms of local beables that we can hope to formulate some notion of local causality. Of course, we may be obliged to develop theories in which there are no strictly local beables. That possibility will not be considered here. So it may be that at the end of all this, you know, people seize this and say, well, I want to consider that, right? I want to consider this thing that Bell says we might be forced to, and I'm not going to consider, namely, a theory with no local beables. Fine. Then just come out and say that at the beginning of your talk and, you know, address the problems that you're going to run up against by not having them. And the way you're going to, you know, what are those problems? Well, I'm going to explain the virtues of having them. So, what is a local beable? Well, it's something that's ascribed to a small region of ordinary space. He talks about ordinary three-dimensional physical space. And you don't want to, you know, if you think a little bit about this, you want to say, well, what exactly does that mean? You don't want to be too restrictive about what counts as ordinary three-dimensional physical space. For example, suppose I say, no, no, like the string theorists, physical space isn't really three-dimensional, it's 10-dimensional or something. Or in Kaluza-Klein theory, right? Physical space is really 4-dimensional and space-time is really 5-dimensional, but this extra dimension, the one you weren't aware of, is compactified and it's tiny, it's microscopic. You might say, okay, fine, right? That's not an issue. Nobody's saying you're forced to work. If you're going to work on a manifold, you're forced to work on a, you know, 4-dimensional space-time manifold. These kinds of things would be easy to do. It would work just as well if you have these compactified dimensions. Well, just as well for what? the question is, what are these local beables doing methodologically or programmatically in the theory? Now, I'm going to go to Bell's account of GRW, where this, again, this is much more general than anything particularly to do with many worlds. And when he presents the GRW theory, he, of course, starts out by giving you the dynamics of the quantum state in terms of this stochastic process. But he says, but I'm not done, right? I've given you the complete story about what happens to the quantum state, but I'm not finished. Why not? Well, he thinks he needs, in addition, for reasons he's already indicated, some local beables. And in this case, he invents ones that Girardi, Ramini, and Weber did not have, because he thinks he needs them. These point events that we've come to call flashes, and they're supposed to occur in ordinary three-dimensional space, as it were, or four-dimensional space-time. Now, what are these flashes like? Well, they're epiphenomenal you have to be very careful about what the word epiphenomenal means, in a causal sense, right? That is, the dynamics of the wave function, the dynamics of the quantum state, which he's already given you, determines the locations of the flashes, and the flashes, in turn, do not have any, as it were, back reaction on the wave function. So you can kind of think of them as floating along directed by the wave function, in the same way that in the pilot wave theory, you think of the particles as floating along directed by the wave function with no back reaction on it. But why does he have to postulate them? Because he wants something locally that exists locally in regular three-dimensional physical ordinary space-time. And why? Right, so this is now, I gave you the beginning of this quote before. Sorry, I'll go back there. I gave you the beginning of this quote before about you can't think of the quantum state as a local beable because it has neither amplitude nor phase nor anything else until a multitude of points in ordinary three-dimensional space are specified. However, the GRW jumps, which are part of the wave function, not something else, are well localized in ordinary space. That is, each of these collapses is associated mathematically with a specific point in. Now, it gets a little tricky here. The xt, I think, is actually a mathematical representation. It's not physical space. It's a mathematical representation of physical space, which is why it's. Yeah. Yeah. I'll get there. So we can propose these events as the basis of the local beables of the theory, and they're the mathematical counterparts. The mathematical counterparts in the theory to real events, definite places and times in the real world, as distinct from many purely mathematical constructions that occur in the working out of physical theory, and all these other things. It's not, right? These are the actual physical things. A piece of matter is a galaxy of such events. And then he gives you a psychophysical parallelism between the distribution of these flashes and distributions of flashes in the brain, which then determine the actual experience. But he doesn't say how that works. He just needs that there be these correlations. All right, so I just want to say a word about, he says, look, you can construct things mathematically, and I want to make this point because I think it will be relevant here, talking to Lev a lot. Take a donut in classical physics, okay? That's made up of local beables, of local stuff. You can mathematically define its center of mass, but its center of mass is in empty space. If the donut's in a vacuum, there's nothing there physically, right? So you can't make the mistake of thinking because I can mathematically construct it, there must be something physical that corresponds to this mathematical construction. Generally, that's of course not true, and it can't be because there are an infinite number of things you can mathematically construct that have no physical significance. Okay? There is no local beable in Bell's sense at the center of mass of a donut. There's nothing there. Okay? Now, you can use a fictive particle with the total mass of the donut concentrated at this point for certain purposes to be convenient for solving things, approximately, but there's nothing physically there. So, to finish this up, and this really is the end, Wilfrid Sellars talks about the manifest image of the world, and he says we start out We have to start out, if we're going to do empirical science, with an image of the world we get without theorizing. Now, this is not the same, I just want to warn people, this is not the same as Eddington when he talks about the two tables. Eddington says, okay, there's the common sense table that's solid through and through, and then the scientific table that's mostly empty space. The manifest image has no opinion about the microscopic structure of the table because you can't see it. It's not manifest, right? It just doesn't say anything. So Eddington says there's a conflict between the common sense table and the scientific table. There's no conflict between the manifest table and the scientific table, even if it's 99% empty space. So this is where the contact is made between the physics and empiricism. You say, look, I've got the manifest image, which I think is pretty reliable information about the world that I start with. I then say, can I construct, and that can be corrected, right? Like the ore in water, I don't have to take that as untouchable, but it can only be corrected by specific empirical pressure put on it. And then I try to construct within my physical theory counterparts to the manifest image. I need to find an image of the world within my physical theory. Oh yeah, so here we are back with Neurath's ship. I knew I had that somewhere. And so what do I need to use here? Well, and this really are the last slides. So here's the overall picture. If you want to have a theory, which at least it's clear how to empirically test it, if it has these components, you can do it. Should be a space-time that coarse grains to ordinary three-dimensional space-time or ordinary three-dimensional space or ordinary four-dimensional space-time. Should coarse grain to it. Maybe it's got little compactified dimensions, that's fine. There should be some local beables that are postulated to be the matter of everyday macroscopic objects. Let's call those everyday local beables. There could be local beables that are not part of everyday objects, like neutrinos. All right, so this is connected to the talk of primitive ontology, a slight spin on it that maybe Valia will agree or disagree with, but I would say electrons and quarks. That'll give you the stuff of everyday physical objects. And then there can be whatever else the theory wants to postulate. Maybe it postulates some local beables that are not part of everyday objects. Maybe it postulates some non-local beables like a quantum state, okay? Why do I postulate it? Well, so I can specify a dynamics that makes the whole thing fit together. And given that, if the fundamental space-time coarse grains to approximately familiar structure, then it'll have models of the dynamics. Could be deterministic, could be stochastic, each of which will contain a distribution of the everyday local beables. The coarse graining of this distribution at everyday scales yields the approximate locations, shapes, and motions of everyday objects at macro scale in that model. And that can be compared to the manifest image. That, I think, is the straightforward story of how physics has always gotten empirical content. Therefore, suppose you have a theory that doesn't postulate a space-time structure with everyday local beables that coarse grains in the way just indicated. Suppose you have a theory that doesn't do any of that. Suppose it's a monistic theory. It only has one fundamental kind of thing, and that fundamental kind of thing isn't a local beable in Bell's sense, like a quantum state. Then I claim, having not mentioned anything about fissioning or probability or splitting worlds, it's not clear how to attribute any familiar empirical content to such a theory. Now, that's just a challenge. But I just wanted to lay it out clearly and explain why other theories that do have local beables in the right kind of space-time do not have this challenge. And that's what I've been arguing for years with Lev about. And that's, oh, sorry. So, prima facie, why? Because prima facie, if you think many worlds theory is presented as a monistic theory, right, and one that doesn't have a fundamental space-time of only a few dimensions, then I think it has this problem with, we need some explanation of how the theory makes contact with the manifest image, and to me it's unclear how that's done. And that is the answer.
So you can talk to the microphone here and give me this microphone.
Oh,
So
yeah. Yeah, okay, I'll use this and then.
Just a very short, thank you very much. It's a nice introduction to my talk. I will address those questions.
Good.
So we'll wait for that.
Hi. So you talked about local beebles, and you said they have to be independent of being observed. Right? But if these beebles exist, at some point, you know, they must depend on how they've been prepared, right?
They depend on I mean, what they are depends upon the physics, the dynamics that got to that point. Sure, if I want to understand what local beebles there are in some little region of space-time, presumably what I want to look at is the physical situation before that and how that evolved to have those particular beebles with those values there. And what happened may have in fact been something we would call an observation, but the physics wouldn't care whether it was an observation or not.
But
Yeah.
now imagine that later there are some measurements and maybe there is an angle of a polarizer or something, some details about how they're going to be measured and not just how they were prepared. If they are defined to be local in space-time rather than just in space at a time, then it would be natural for them to depend also on the future, not only on the past, wouldn't it?
No, I don't see why. I mean, the normal causal structure, the causal structure certainly in classical mechanics is from the past to the future, right? You specify the past and that, you know, you've got differential equations in time that evolve the thing forward in time.
Of course, right. So Bell made an assumption about the arrow of time, which is a very strong assumption, and it's a very natural assumption. And it implies that the future does not exist at all when you look at a point in, but if you take a block universe view, which is some physicists do some of the time, and there are some theories that work in that manner, then this assumption of the arrow of time would not hold.
Okay, so again, this would be a long discussion, but let me make the key point. The term block universe, unfortunately, if you go and look, and I don't know who originally used it, but if you look at when Hugh Price defines it, it literally has two completely unrelated clauses. One clause says, essentially, there's only one past, there's only one future, there's only one present. Yes, I agree with that. Does that make me a block universe person? The other clause says, by the way, there's no direction of time. Now, those have absolutely nothing to do with each other. I can believe, I mean, there's a trivial sense in which the future doesn't exist in the sense that it doesn't yet exist. That's why it's the future. There's a trivial sense in which the past doesn't exist in the sense that it doesn't exist anymore. That's why it's the past. As far as I'm concerned, there's only is, was, or will be one unique past and one unique future. That's a block, if you like. But I think time goes forward, and I think causation goes forward. Now, if you want to be a retrocausalist, right, fine. If you want to say, I think there's not only causation going from the past to the future, but retrocausation going from the future back to the past, fine. Then say that the first sentence in your presentation, and then worry about loops, because you now have loops, right? You have causal loops. Because apparently the present can affect the future, which can then back reflect on, and then even mathematically, you're in a much more difficult situation, as for example in Wheeler-Feynman, just even mathematically, to write down equations to solve them if you have loops, right?
So unfortunately, I cannot bring you back to my lecture yesterday, but I did start from just this assumption. So I assume that there is a signaling arrow of time, so the symmetry is going to be broken, but other than that, it doesn't mean that there's no retrocausation.
You want to ask the next question?
You started with a canon, and I think it's very helpful to say that canon has a beable where it is in every moment of time, but also you said how we know that it is. Maybe it's in the dark, whatever. And I think physicists say that canon in particular place, because when it hits, it puts some sound waves and light waves and maybe neutrino going through and slightly changed. So if we look at all these different things, all the effects the canon do on other people, then we know the canon is present. And we might, it's useful to say, oh, there is a beable canon in particular place. But we can take all these other things, the counterfactuum. In every way we try to measure, we'll find this canon. And clearly, it will be much easier in quantum mechanics if we'll put these local beables on everything. But we don't have to. If we assume that there is a wave function, this wave function, maybe there is also some problem. A single quantum object, you cannot find the whole quantum state. So first way, you can put it protect it in some ground state. And some people will argue maybe it's not good. But quantum mechanics tell us that every preparation gives us the same quantum state. So I think it's logical to say that we need many preparations to test the quantum state. But the measurement, we will find this quantum state. And we know the effect. So we have to put beables. It will be easier for philosophers to say that the canon there or some flash is there. Or you can say, no, there is just this quantum state. And the quantum state gives the effects which we know. We don't need to, when we go to a laboratory and we want to explain what's going on, these flashes are not needed. All what is needed is just the quantum state. So one could say the only thing which exists is quantum state.
Well, okay, again, it would take a year to unpack everything in that. But let me hit some things you did at the very start. You mixed together two questions. One question is an epistemic one. On what grounds would a physicist say there's a cannon somewhere, or let's say a cannonball hit somewhere, right? Epistemically, why would they think that? Well, they heard a sound, and it sounded like it came from over there, and then they see a dent in the ground, and the dent is there, and then there's a flash, and blah, blah, blah. Well, look, that's of course the kind of empirical evidence we would use to say, to justify the claim that a cannonball hit here. But the physics is that the explanation goes, the reason you heard that sound, the reason you saw that flash, the reason there's a dent here, is that the cannonball was here, right? It's the causation is from the cannonball to the effects, not from the effects to the cannonball. Yeah?
The quantum wave of this cannon.
Well, the quantum wave for this cannon is not in physical space. So I don't know how a quantum wave can make a dent in a floor.
No, there's a whole interaction. We live in 3 dimensions, and all what we observe in 3 dimensions, and macroscopic objects interact in 3 dimensions. Everything in 3 dimensions. This quantum object, you say donut, and you was upset that the center of mass of the donut is empty. Yeah. Yes, but ask where was the donut? You can define any other way. Of course, the center of mass position doesn't mean, but if you want to ask where is this donut, where is the gravitational field of this donut, it's well defined. So it's all in 3 dimensions. The donut interact with everything else in 3 dimensions.
Right.
Even it's a quantum state of a donut.
Again, I'm just going to make something I take it people will agree with. Lev, your understanding of many worlds is non-standard, at least with respect to the understanding I've always heard from, say, Simon or David Wallace, okay? Because you do say, oh, it's a 3-dimensional world, stuff happening in a 3-dimensional world. You seem to not entirely believe in a quantum state, not as I defined it. And I'm just saying, if that's true, that's fine. That's kind of the opposite of the way it's usually presented, which is that the only thing you believe in is a quantum state. And you're trying to derive everything out of that. So at least when you say, yes, stuff happens in 3 dimensions, you kind of shrug and say, of course it does. Fine, that's good. I don't quite understand how your entire picture fits together. For the reason that I don't understand how you regard, I don't really even understand quite what the ontology or theory is. But this is just to explain what needs to be made clear to me from my point.
Maybe we should.
Thanks, Tim. Let me connect to the manifest image of its methodological role. So I agree that our experience is local, the experiments we make are usually local. So locality is there at the level of the explanandum. Now we need to ask, does it have to be there at the level of the explanans? So I think that when we look at physics in general, it would offer us 2 strategies to explain this locality at the level of the explanandum, either because of local beables. There is something there which is local. But the other strategy would be based on dynamics, dynamical law. So we have non-local beables, and they explain this manifest local image using non-local dynamics, and I think that you can read just many worlds in configuration space, you could read it as doing this, taking this strategy in a way that seems to me fine, wouldn't it?
It seems to me you're giving me a false dilemma. A pilot wave person certainly agrees there's non-local objects and non-local dynamics, and that non-local dynamics governs the local behavior of the particles in regular physical space, and that's part of the explanation for why we see what we see. If you say, look, the only fundamental space there is this thing you call configuration space, and as has been pointed out many times, you better stop calling it configuration space, because it isn't. Configuration space is a space of configurations, and configurations are abstract descriptions of collections of objects in a lower dimension space. What you mean is that couldn't the fundamental space not coarse-grain to anything that looks like regular space-time? And all the stuff that's going on is going on in this higher dimensional space. Maybe there's just a quantum state, maybe there's a quantum state and the marvelous point, as Shelley calls it. That's a theory of something, right? It's a physical theory of something. I just don't know how to make it a physical theory that corresponds to the world we live in.
Yeah, so I didn't have pilot wave theory in mind, so there you could interpret it as having both a non-local beable and a local beable, and that's okay. But even if we drop this local beable, the Bohmian particle, could say, well, there is this configuration space or abstract space or whatever, and the only thing which coarse grains it and makes it gives it a 3D appearance is the dynamics, the dynamical law, which maybe you could interpret it in a non-Humean way. It's also part of your ontology, but it's not a beable.
Yeah, so there are two, I mean, you're following David Albert's approach here, and there are a couple things to say about it. One is, it's one thing to say, well, it's just the dynamics, but there's a whole lot to fill in about how a dynamics on this high dimensional thing would, as it were, create an emergent low dimensional thing. And the other thing is, of course, there's also the question of explanatory structure, right? I think what explains the dynamics, like the structure of the Hamiltonian, what explains it having that structure is the geometrical structure of the low dimensional space.